question. Yes, we have a question.
I have a question about air and stuff.
Air and stuff. Okay.
So if you have an enclosed space,
Okay.
how do you get the air in there? Where did it come from?
Like a basketball. You put the air in through a little needle. You lick the needle and you stick it in the basketball and you fill it up, right?
No, but what if the box is sealed?
You open it up and then you seal it back up. Do they make coffee flavored vodka? Because it's so well, you can. I've heard.
You have Irish coffee? Not your granddad's coffee.
Okay. Let's talk about definitions here. And why is this 3 and that's 2? Because it's 3, insets. So 2 definitions.
One was air depth and it's 2 makes sense.
Yes, but I know somebody was going to catch me on that. All right. So this goes back to what we started talking about. So a ground boosted engine. All right, so what is a ground boosted engine? That is an engine that has a manifold pressure above atmospheric on the ground. An engine that has a manifold pressure, MP, above atmospheric. On the ground. So that is your turbo supercharged, if you will, right? It's been boosted. So if I say ground boosted, that's what you got.
So the reason those have gears is because, like, some of them have different gears. It's because it'll taper off before.
Well, they have gears?
Like, some of them have different tiers of the supercharger.
Okay, so if we were specifically talking about a supercharger, now I just said ground boosted. So turbocharger, no, it won't have gears, and we'll get to that. But yes, engines that have an internal supercharger actually have multiple speeds to them. So they have not just one. So ground boosted. Okay, then we have turbo normalized. Sometimes called an altitude engine. I don't particularly care for this. This term, mostly because I can't equate it to something that wants to make sense. But turbo normalized does make sense to me. It's just making the engine normal. So that is a type of engine that uses a turbocharger or supercharger. Well, I shouldn't say that because I'm going to call it turbo normalized. We'll just leave it as a turbocharger. An engine turbocharger to generate sea level pressure in the in the intake up to its critical altitude. So again, that's an engine that on the ground at sea level, the turbocharger lets the engine think that it's on the ground at sea level. And then it goes up to 1,000 feet, and the turbocharger lets the engine think that it's on the ground at 1,000 feet. And as it climbs, it's going to keep letting the engine just think that it's at 1,000 feet, except for if you're constantly keeping the intake manifold, it will say 30 inches. You go up higher, 30 inches, up higher, 30 inches, up higher, 30 inches. What's the trade-off that nobody's really talking about here? Well, we are now.
More fuel consumption.
Okay, guy's cheapskate. Always thinking about his fuel consumption. Yes, more fuel consumption, but you have more power, more speed. But what is the trade-off here that is you're generating heat? So the air is getting inside the intake manifold. The air is getting hotter and hotter and hotter and hotter. So are you really keeping the exact same horsepower on the ground as you are at 15,000 feet? The air is much hotter, so it's expanded, so it's different. Yes?
You're also going up in altitude, which has lower ambient temperatures as well.
Not by enough to compensate for that. You're getting closer to the sun, so that's not true.
Okay, Chris.
Yes, Steve.
Is it set at for sea level all the time, or can you set it for different altitude?
No, it's set for sea level. Yeah. All of these controllers. We'll talk about the controllers, which get a little complicated, but they're all preset. But there's different ones, and they all do their job, and we'll get to that.
Isn't prop efficiency a factor?
Is what?
Prop efficiency?
It's always going to be a factor.
So wouldn't that be another major?
Yeah, but I didn't want to go into that. But then again, can the airplane go faster because the wings have less drag on them?
Technically.
So there we go. So we got some give and take. Yes.
So I was reading about like aftermarket turbo normalizers from planes.
There are, yeah.
And a lot of them said like not to use unless like over like 4,500 feet or different things like that. Would those still normalize down to sea level, or would they just normalize to like 4,500?
Do not use below 4,500.
Yeah, I read stuff. I don't know.
I'm not sure on that one. And I think once we get into how these things work, you might be able to even figure out why it would say something like that, because it takes quite a few controllers to make them work. And then you run into some more problems. So things... All right, so up to critical altitude. Well, let's define critical altitude. All right, critical altitude is the altitude at which an engine no longer can produce sea level horsepower. The altitude at which an engine can no longer produce sea level horsepower. All right, so Tyler informed me that he did listen to the automated weather service here today. About what time?
I didn't listen to it. I calculated.
Oh, we calculated it. Same thing.
Maybe 2,130.
So he calculated that today our density altitude here is 2,130 feet. But we're really at what altitude? 75. So that's just strictly because of heat, or mostly because of heat. So I go and I grab my little 150 and I pull it out of its hangar and I get in. What is the critical altitude for me today? What's the definition of critical altitude?
Gonna be on service ceiling.
No, not service ceiling. What's the definition of critical altitude?
Oh,
It would be underground, flyways.
Okay, so the altitude at which an engine can no longer produce sea level horsepower. So today, if I would have decided to go flying and the density altitude here is 2,100 and some odd feet, at what point would I have reached my critical altitude?
Before you even take off.
About the time that I pulled up to the aircraft and saw it. I already exceeded it. So the point being, because even on the ground, the airplane already thinks it's at 2,100 feet. So it's already exceeded its critical altitude. So if it's a 100 horsepower engine, am I getting 100 horsepower today? Nope, not going to do it. All right. But assuming that it's a standard day and it's 59 degrees or 15 for you, and I listen and say, then the barometric pressure is 29.92 today, and I'm at sea level and I take off. At what point do I reach my critical altitude?
The moment the wheels take off.
So pretty much, as soon as I get it 1 foot up. All right, so to something Prince was asking a little bit ago. Remember I told you about how to determine if an engine with a fixed pitch propeller is producing is proper rated horsepower. How do you do that?
RPMs.
What's that?
The RPM drop.
Static RPM.
Static RPM, not drop. Static RPM. So I feet on the brakes, full throttle it, look at my RPM. Now, when would I do that? What if I would have done that today when it's 92 degrees outside at 2100 feet? How do I adjust it? Because it just says static RPM in the type certificate data sheet. Static RPM for this prop equals 2375 RPM, 2375. So what?
Do they have a chart for density altitude
Good thought? No.
as a range for
Come on, Prince. You're my guy.
Repeat the question.
Okay, so is the air, so we're trying to figure out if the air, based on static RPM, I have a range in the type certificate data sheet that tells me if the engine is producing its rated horsepower. But there's no correction for temperature, density, or anything. Why? Is it the same? You're saying it shouldn't be the same. Well, let me ask you this. So today, if it's 90-some degrees outside and the density altitude is 2,100 feet, is my engine producing 100 horsepower?
No.
No. But yet I tell you this, if I were to pull out my type certificate data sheet and says the RPM is 2375 and I tried it, guess what RPM I'm going to get?
2375.
I'm going to get right in that range, assuming my engine's still working. Why would it have worked?
The prop has less
Because-
drag.
Got it? What?
Less drag on the prop.
Less drag on the prop. All things are equal. So the prop is also not biting as much air as, if you will, so the two match each other out. So the static RPM always is the static RPM based upon the propeller. That's why it changes by the propeller. So you wouldn't do that and go, still making 100 horsepower. Look at the RPM. It's not. It's actually less horsepower. The prop is just working less up front. So the engine didn't have to work so hard, so it still appears that it's giving you the same horsepower, but it's not. All right, so critical altitude. Let's see. What else do I have in here? Well, normally aspirated. In normally aspirated engine, that altitude is anything over sea level on a standard day. So as soon as you take off, you're already losing horsepower. But in supercharged / turbo, that altitude is much higher. How much higher? It depends on the engine and turbocharger and its condition. And I think most of them are about 15,000 feet.
On bigger engines, is that more or less?
It's going to depend on how big the turbocharger is. Turbochargers are all different sizes, and
Do you have turbo on your plane?
oh, it's a little Cessna 150.
it's not an aftermarket.
I mean, not to point fingers, but he doesn't even have turbocharger on his plane. His plane is way nicer than my plane.
You can do it after market if you want.
But he doesn't want it because he uses more gas.
All the money went into those screens.
I was gonna say leather seats. Yeah, we're making fun of your really nice plane. We're a little jealous.
It is a really nice plane.
I know. All right, where did I leave off here? Critical. Okay, supercharging. So we talked about ground boosted, turbo normalized, critical altitude. Now we'll do supercharging. Supercharging. That is supercharging. So notice the ing on the end. Supercharging is boosting the manifold pressure above 30 inches of mercury, because that's now boosting it over standard temperature or standard pressure, which is kind of the same thing we talked about ground boosting. Same idea. Not same idea, it's same thing.
What's the limit for that?
What's the limit?
I think 60, 50.
Oh, it's totally it's an engineering design of the engine. A lot of engines can't handle much. Some engines handle a lot. Yeah.
Going back to the fuel usage with the turbochargers, do they actually inherently use more fuel? Or, like, so when you're at altitude, you lose the less power. But if you had if thought it was at sea level, couldn't you just throttle back and fly at the same flight speed and use the same amount of fuel? Would that not work?
I'd have to think that one through. But I think Juan's point was made that because your air is more dense, so dense air, more fuel to get your near stoichiometric mixture, so it's going to use more fuel.
It depends how fast you want to fly.
And how fast and all that stuff. So.
So with ground boosting and supercharging the same thing?
Yes, but as I'm looking at my notes, I should have put supercharging / supercharger. No, I don't want to do that because I'll do it the next one. So yes, I'm just going to say yes, and I'll tell you what, I'm going to change my notes just a little bit, say supercharging, boosting the manifold pressure above 30, and then I'll say this, supercharge. So one thing is a verb and one thing is a noun. Supercharger, that is a belt. I was going to say, not on airplanes, but wait, belt or gear driven.
They use chains on superchargers as well.
Not that I've ever seen, but
Not nowadays.
belt or gear driven compressor. That boosts manifold pressure. I would just say boost manifold pressure. Honestly, all the superchargers that I know of, they on all the planes, they do boost manifold pressure over 30 inches. I'm sure there's something out there that I'm not thinking of, but if you look at some of the engines like the Lycoming round engine, the R680, it has what looks like an internal supercharger, but it turns at a speed that doesn't boost, it just mixes the air. So they call it a diffuser. If they would have spun it faster, then they would have called it a supercharger, but it didn't work out that way. Or they didn't want to. All right, so let's see here. I think that's just gorgeous. Oh, that is a centrifugal supercharger of a Bristol Centaurus radial aircraft engine.
That's misspelled.
Which one? Which word? Which word is misspelled? That one?
They spelled it differently for marketing.
Oh, okay.
That's a sleeve belt engine.
Well, there you go. See? I don't even know what this engine is. But I thought it was beautiful when I was looking for something else and I saw that. I'm like, oh, I just have to show that because it's just a work of art. All right. This is the two-stage supercharged Allison engine of the P63E, this version. So this one, I don't know if I want to get into this right now. Two-stage supercharger. So two-stage, and you guys should know this, two-stage means two compressors, just like a turbine engine. So we have a big one and a small one. So without even looking at the flow, if I have a big compressor and a small compressor, which one comes first? Big one. Okay, so it compresses it here, goes through, compresses it again, then off into the intake manifold. So we have that. Let me see. Oh, and just for fun, even though Prince will probably tell me I'm wrong, because this is not Dago Red. Is that plane still in existence? No. This is what I read about this. I don't know how true it is. Dago Red, for example, gets 75 PSI boost with a manifold pressure between 140 to 150 inches of mercury. And this is out of a 1,650 cubic inch V12 Rolls-Royce Merlin engine. That's a lot.
It's modified.
It's slightly modified.
Jets, right?
Day one, you worried about the fuel consumption on this one?
That's just speed fire.
That's the P51.
Is this the one that has like Lear wings on it? Didn't they put like Learjet wings or something? I don't know.
They modified the wings a lot.
Yeah. All right. So anyway, I just saw that and I thought, wow, 75 pounds per square
So
inch.
based on your formula, that would be 2 gallons a minute.
Okay. It's slightly insane. All right. This is what's called, sometimes you'll hear it called in aviation a roots type blower. And where that's actually going to come into play is stuff like this, or something very similar to this, is actually used in some older aircraft pressurization, for the cabin pressurization. And of course, I think if you have something like that, you're probably not going to have turbine engines on it. It's doing this. So anyway, and I thought, there's no such thing as a bolt-on supercharger for an aircraft. And then look what I found. So what is this right here? Come on, you guys know what that is. It's just a Lycoming engine. Come on, it's just like the one you guys built, right? It's not. It's.
I'm not gonna lie, Kevin. It looks like he copied and pasted that.
I did not. I found this on the. I found this on the Google. It's actually a G3i supercharger. Look it up. AOL it, man. G3i supercharger. And I stole this a couple. And this is what it is. This is the bolt-on right here. See, that's bolted on over here somehow. I don't know. And I don't know, the carburetor is going to go somewhere on there. But it's just, that's what's inside. And it's these things. Huh? Did you look it up? There it is. Now you're going to accuse me of actually going online and making this up for you guys. So it has a 20,000 foot critical altitude. What does that mean?
It doesn't move power until it goes to
20,000 feet, and then it stops making
That's a
sea
cap.
level.
It blows up at 20,000 feet. What? What happens after 20,000 feet? It starts losing horsepower. So all the way up to 20,000 feet, it's going to produce, based on what I see here, this engine is at best an Lycoming 0360, IO360 parallel 180 horse engine. Is that what you have? Yeah, so there you go. Right there. You have yourself a supercharged Cherokee.
Probably cost more than
I can't even imagine. And some of these, whatever these are over here. All right, so that's what we, only if you get caught.
Nothing's illegal until you get caught.
That's right.
only after you crash.
It's when does it become a problem? After you crash. All right. So we have supercharger. Let's see. I'm not going to write that Dago stuff on there because that was just for fun.
Can you
All
hear
right.
those in line like you can on a car? Or the
Can you what?
Can you hear the supercharger?
I've never even imagined that existed until I saw it online, and so I don't know what it would sound like with the propeller, but
Pretty cool.
you probably can.
Well, the Merlin is pretty noticeable.
I was gonna say some of those.
Feel of it.
Yeah. All right. So let's throw out a couple more definitions just to make sure we're up. Turbocharger, and that's an exhaust driven compressor. And I've got turbo normalizer again. I've got turbo supercharger again. Manifold pressure and upper deck. All right, so we already know what all those are, so I think we can kind of stop right there with that one. And that kind of covers some definitions. And what is the whole purpose? That is increased manifold pressure. Well, let's see, let's think this through. Increase or maintain manifold pressure. There we go. I like that. So increase or maintain manifold pressure. If we increase the manifold pressure, what do we do in horsepower? All right. Let's see. What else does it do? It increases the weight of the fuel-air mixture delivered to the engine. There we go, Juan. There's your extra fuel burn. Mock him, but here's a guy who flew across the Atlantic, so he knows what he's talking about when he talks about fuel burn. So increase the weight of the fuel air mix to the engine, which keeps our horsepower where we want it to be. And also, we could say it increases the compression pressure. Gee, and I hate to bring this one up, but let's remember that. Does it change the compression ratio?
Yes.
Thank you. I hear a no over here. Who said no? Good for you. So compression ratio is constant. What is the compression ratio? Anybody care to define it?
The volume difference between the top dead center and bottom.
All right, there we go. Difference between the volume of the piston at bottom dead center versus top dead center. Does that change?
No.
Nope. So the ratio between the piston at the bottom, the only way I can change it is to change pistons, rods, crank throw, something other than that. So, all right. So the greater the pressure, well, I could write this for you. The greater the pressure in the cylinder at the beginning of the intake, the greater the compression pressure at the end. But that's not changing the ratio. It's just saying if I can make more air into the cylinder to begin with, I'm going to have more pressure when it piston comes to the top. So the greater the pressure. Thank you. Volumetric efficiency at work for you. The greater the pressure at bottom dead center, the greater the pressure at top dead center. And that means more
Volumetric efficiency. Sorry.
That means more. Hannah's with me today. Power. Why does it make more power?
Plank.
Thank you. Finally. Remember Planck?
These are the things you can change to get more volumetric efficiency.
No, volumetric efficiency is now turbocharger will or supercharger will give you better volumetric efficiency because you're pushing the air into the cylinder now instead of letting it be drawn in.
Wouldn't turbocharger though reduce it?
Volumetric efficiency?
It would inhibit scavenging.
To a point, yeah. So that's different. So you're still forcing air in, so that's better. Yes.
So, what effect does the density of the air have on? Also, as you go,
You have to speak up for the mic.
The props having to the engine not having to work as hard to turn the prop the same number of RPMs because the air is or less dense.
As you go up in altitude, right?
So if you set if you normalized it and
Okay.
set the throttle and started climbing, wouldn't you or say at 4,000 feet versus 8,000 feet with the throttle same at 4,000 feet?
Would it take, okay, so you're saying yes.
RPMs would be higher at 8,000.
So if it takes, well, let's just say it takes 120 horsepower to turn your propeller at 2,300 RPM at sea level, how many horsepower does it take to turn it at the same RPM at 4,000 feet, right? Less.
So,
We know that just based upon how an aircraft performs on
Do you
static.
be careful of going over red lines?
And you have to be careful going over red line. Well, in a fixed pitch propeller, yes. In a constant speed, no, the governor should handle it. But there's always that risk. So, all right, plank. What was plank? P is, shouldn't even have to write this down, you know this. L is,
Length of stroke.
can we change this?
No.
Can we change pressure? Yes. All right, we can change pressure. Length of stroke in feet. Don't forget that. A is area of what? Piston. Area of the piston. Can we change that? No. N is
Number of cylinders?
RPM. And K is
Number of cylinders.
number of cylinders. Yeah, you laugh, but you remember it. CYR.
That's the only reason why I remember it.
Cylinders. All right. So if we can change the pressure, we change the horsepower. So add pressure, we make horsepower. And we just proved it with our plank. I have a little example here. I'm not going to take the time to write it down, but where a certain engine is at 30 inches is 550 horsepower. Note that there's about a 1 inch loss across the carb, so 30 inch is possible. So 30 inch is impossible without a supercharger. But I'll just do this. Sidebar. So we had 30 inches, made 550 horsepower. So at 35 inches, it ended up being at 700 horsepower. So this is just changing the pressure here. Same engine. If I could get it up to 40 inches, I would get 875. And if I could get it up to 45 inches of mercury, I would have 1050 horsepower. How many horsepower does your Prius look-alike have? Has nothing. All right. Would you say it has no horsepower? Is that what you said?
I don't know.
Oh, they said it had no horsepower. Because we could get one of those little bolt-on kits for that thing. All right. So, increase the pressure. It works.
Now, the manifold rating, okay, military ratings, say, like, they have a chart like that, and they have different model numbers.
Have what? Say it again.
They have different model numbers for the different manifold pressures. Why would you do that? Just for different usage?
Why does I'm lost you on this one.
Okay, so I have this military book.
Have a military book. Okay.
It's U.S. Army Airport,
Okay.
so World War II.
Right.
And it has it has the same engine
Okay.
and different model numbers.
Oh, I got it. So exact same engine, different model numbers, and those different model numbers actually have different limits to manifold pressure. Okay, so one of the things that you'll find with most turbocharged aircraft, they are low compression engines. So if you change the compression ratio at all, you're going to change what you can do with the manifold pressure.
Okay.
So it's probably a piston change, design change, or as they progressed in metallurgy, stronger rods, things like that, then it would
Okay.
change the compression ratio, change the strength of something. Because at some point you're just going to blow the cylinder right
I've
off.
seen those exact numbers in that book.
That's probably where I got it.
Okay,
All right.
One question. You know Tornado Alley, the people that make the...
Yeah.
Who is right? Because I called Continental and they said, no, you cannot add that. If you want to add that, it's up to you, but all the warranties are off. We didn't make this engine to be turbo normalized or... And then you go to Tornado and they say Continental doesn't know what they're talking about. We never exceed sea level pressure, so they're wrong. And their guarantee is useless anyway, but I just don't know who is right and who's
So
wrong.
you're trying to get me on the record here on this one? As a former engine builder, If I would have built your engine and you would have called me and said you're going to add this Tornado Alley turbocharger, I would have said my warranty's off. Why? It's because just you're. I don't know. If it's always, we could just think it through with what we've learned so far. You are keeping your engine just at sea level, but you're adding back pressure because that's a bolt-on turbocharger, right? I thought you were talking about they used to sell these weird things that claimed they made a tornado, and it was this little stainless steel thing you put in your air cleaner when you're a goofball. All right, but we know that we're going to add back pressure. So to run the turbocharger, so the back pressure is going to change scavenging. We know that is going to put more stress on the cylinder. We know that I assume the system comes with its own exhaust. It would have to, totally different exhaust. And then we know that because we're compressing air to put it in, it's going to be hotter. So we're going to have hotter air. Just maybe those little things involved there are going to take their toll. And so the engine manufacturer just as soon not warranty a bunch of valves or something in that case because there's a little extra stress on it, especially if it's an engine that's already prone to some valve problems to begin with. It's like, oh man, just add that to the mix and it just makes things really more difficult.
If you were to do that, would TBO be shorter?
It would actually, I don't think it would be unless you're buying this kit and then the kit would be part of the supplemental type certificate, would have included in it instructions for continued airworthiness, and the instruction for continued airworthiness would tell you if it's a shorter TBO, but he's flying Part 91, so you don't have to do TBO anyway. You don't have to do it if you were flying for hire or something like that, and at that point, I don't think I'd want to. I don't know. That's a whole other thing. Yeah.
Why would you use a turbocharger over a supercharger?
Why would I choose one over the other?
Yeah.
Okay, so as a manufacturer, or
Well, when I'm thinking about it, we're scavenging for a turbocharger. It's going to be probably more expensive because of the heat on the turbine wheel.
so here's the theory that I would go with. You're wasting a lot of heat out of the exhaust. This is where this comes from. So we have a heat engine, and we're only using, 33%, 30-some% of the heat to make power. The rest of it is being radiated out from the cylinders, and a large part is going out the exhaust. So we're wasting it out of the exhaust. So if we could bolt something to the exhaust that somehow recaptured some of this wasted heat energy and put it back in the engine, that would be awesome, right? There's your turbocharger. Now, if we took a supercharger is belt-driven or gear-driven, does it change the exhaust? It's actually robbing horsepower from what you've created. Now it's got to drive a gear that's got to drive that, so that creates a problem. So I think that would be the choice of a supercharger over choice of a turbo over supercharger. But then you can turn it around and look at most radial engines. Modern radial engine, if you can say modern radial engine, they use internal superchargers and not turbochargers. Why? Because it was just easier to build it inside the case. It also diffuses the fuel, so it gives you, and you can do 2 speeds or multiple speeds, and so there's trade-offs to everything. But try and put a supercharger on a horizontally opposed engine would be a little more difficult. Yeah.
So what did they do differently? Like, say I wanted to, like, I used to 360, but I wanted to buy a new one for light one, and I got like a turbocharger.
All right.
TO 360. What is different on that engine?
So you want to what? So what's the difference between like an O360 and a TIO 360?
Right.
Well,
As far as like you said, the turbochargers can cause more the back pressure, more wear on the valves. Do they do anything to?
based upon my experience and not knowing the exact engineering answer, lower compression pistons. Probably a little bit different piston design, different piston part number, more cooling fins on the back. Definitely, I think that engine would have piston cooling nozzles. Small differences like that. I don't think I don't think the raw cylinder is any different, or the case, or the crank. Just nuances.
There's a lot on taturbo.com about tornado turbo.com.
Okay.
I think they answer your question there.
What he-
Turbo.com.
T8turbo.com has like what are the differences. And all right, so we have some limits with supercharging. Supercharging is great. We can't just keep turbocharging, right? At some point, we're going to have a problem. So one of them is temp. Temperatures. As we said, as air is compressed. Air is compressed. Temp rises. And of course, I'm going to have to kind of start cutting out some of the little notes here. I think I'm being redundant and we're running out of time. As temp rises, as crest, temp rises. When the temp rises, then the density of the air goes down, and that's bad. Also, increased air causes a risk of detonation and I don't want to say pre-ignition, but it's certainly light off the, get to a certain point, 500 degrees, and you're going to light off the fuel in the intake manifold. We have an engine design limit. At some point, you're going to run out of stuff here. I think this is kind of interesting, and you guys seem to be sort of really tuned into this stuff. So I'll tell you, for a 710 horsepower engine, to get 1,000 horsepower, so that's an additional 290 horsepower. So thing is, I got a 710 horsepower engine and I really want to get 1,000 out of it. Okay, so I got to do something to it. So I say, oh, I'm going to get one of these bolt-on superchargers. It takes about 70 horsepower to drive the supercharger. All right, so I wanted to get to 290. So that's 290, which I wanted to get. Plus, I got to add the 70 that I'm going to use to drive the supercharger. So that's going to equal 360 additional horsepower to get the 290. So you're really asking a lot from an engine that was designed for 710, aren't you?
Do you ever build engines that people call and ask about putting a supercharger on for them?
No. All right, let's talk about an internal supercharger. All right, what is it? Well, it consists of, I said, a gear-driven, could be belt, but that's pretty rare. It's that funny thing I showed you. Gear-driven, centrifugal compressor. That's the way most of them are. Which could also be called a diffuser. Or consists of a centrifugal compressor and diffuser. So the fuel-air mix is drawn into the compressor. So what's entering the compressor? Fuel and air. So before it gets to so after the compressor, it's got fuel and air in it. And I make that point because you have to think about aircraft that have cabin pressurization. Where is the cabin pressurization going to come from? Well, if it's a turboprop or jet engine, it's just going to come off bleed air, right? And bleed air is before the fuel is added. But if you have a big radial engine that has this giant compressor in it, this giant supercharger, can you use that to pressurize the cabin? Thus the Roots blower that I mentioned. You got to do something different. You can't be running fuel and air in it. Just rob it off there. But in a turbocharged engine, it's different. You actually use the turbocharged air to pressurize the cabin.
Kevin, so this isn't one of
That's right, because in the internal superchargers are almost always on radial engines. So in a radial engine, it's inside of the case. You can't see it, and it's between the power section, usually in the accessory section, in between the two. And so you have your pressure carburetor on the bottom, because these usually have pressure carburetors at this point. And as we saw in the drawing, the pressure carburetor is atmospheric air, comes in, pressure carburetor, fuel, air. Next thing is the compressor, the centrifugal compressor, off to the rest of the engine.
So, you need a specific carburetor for that, don't you? You can't compress a fuel, you can only compress air.
Do you need a specific special carburetor?
Yeah, like a...
PR58's fine. PR58's used on
the
that.
same?
Pratt & Whitney 985. What's oh shit, I'm not even sure which carburetor that. I think that's a small pressure carb. I'm not sure. But
So if
no.
you were to, because the fuel air mix is going to change as you can... No, never mind.
All right. Let's see. The compressor. Fuel air is drawn to the compressor from carb. And we'll say thrown out. Into diffuser. And of course that provides better fuel air distribution. And from the diffuser, then it goes to the intake pipes and then to the cylinders. And let's think here. And I mentioned that the diffuser, the supercharger is usually in between the accessory section and the power section. And we already talked about a little bit that some of these superchargers are actually two-speed. For example, the Pratt & Whitney R2800 used a two-speed compressor. So at low speed, it was 7.29 to 1, and then you could shift gears. And high speed, and depending on the model, I believe, 8.5 to 1 or as much as 9.45 to 1. So you had a little shift into high. So you're going to fight the bad guys, you'd switch into high speed. Because the compressor is directly tied to the engine, that means that it's directly tied to the RPM. There is no need for any controllers. It's engineered into it. They say, well, if the engine's turning this RPM and the compressor is turning this RPM, the pressure will then be this, because they're tied together. Not so with turbochargers. They're completely independent. The turbocharger can spin like crazy and the engine's not doing anything. You're like, whoa, that's a problem. So you're going to have to add all these controllers. So we will stop here, and tomorrow we will pick up with turbochargers. So don't go away mad. Just go away.